Hello and welcome. Today I'll show you a bit about Visual Studio and some image processing. And I'll just run you through the basics. As you can see here, we have two variables, width and height. They're already defined in the header. I'll get back to that later. That just tells you what size the video feed will be at. The video grabber, it's just it grabs the camera to be used, and in this case it's the integrated webcam. These are the output video, and they are also defined in the header file. I'll show you in a moment. And down here we have the video text to allocate, width and height, and in this case GL, RGB, which are colors, and also for the luminance, we'll use that later. That's basically grayscale. The GL converts it to a floating point and assembles it into an RGBA element by attaching one for alpha. Yeah. These are just some basic kernels that we'll use for the filter, and I'll also show you later when I get to those filters. Down in the update, you see the unsigned jar pointer at the pixels. It basically stores the value of the pixels from the input image for later use. And I've built the entire thing as a switch case, meaning that I changed the filter number to show you each different filter, and that's basically it. Now the header file, it's just a place where we store all our variables and different textures. These are the textures to just display the video feed. That is the frame. And as you can see before, width and height variables is here, and that was defined before. And just our basic filters. Great, let's begin. And one thing I forgot to mention is the test app draw. This tells us the location of where the output video feed should be displayed on the OpenFrameworks program. You'll see in a moment. And you can see the first row, which is our output video, is located at 2020, and the next one is located right next to it, because we have the width plus 20, so it'll just the 20 plus the width, so it'll just place itself right next to it, to the right side of it. Yeah. So the first filter I'll walk you through is the inverted filter, and it's a kind of filter of point processing, and it's very simple. We just go through a for loop and showing through each pixel, and this takes every third pixel because it's RGB, and this little line here is what makes the difference. It takes the negative value of the pixel, so to speak. If you have a pixel value, it subtracts that value and it gives you the negative value. That's why it's also known as a negative filter, a negative inverted filter. And basically it looks like this. Let me try to run it. It's a bit slow. In the meanwhile, let me just show you. As you can see here, there we go. Yes, and this is basically what it looks like. So my red becomes bluish, and white becomes black. And this is because, as you can see here, the inverted color, if we have sort of green, it will become an entirely different color. And that's basically the inverted filter. And the second filter I like to show you is the RGB to Grayscale filter. It's also, as you can see, a basic for loop, looping through the pixels. And here, just one line. Everything happens in one line. Output pixels from I, as that is the pixel for red, and the pixel for green, +1, and the pixel for blue. And that's already what we've defined previously. Well, of course, the computer knows that the pixel number 1 is I, because it's got the RGB spectrum in G and B. And if we divide all these with 3, we will get the grayscale value. And that basically looks like this. A bit 30 film noir style image. So I forgot to mention this little line here. It's simply what outputs the image in the new position. It also writes the texture to the subsequent withdrawal of its on screen. In this case, with the RGB spectrum. Yes, that's basically it. So number 3 is a simple grayscale to binary, and as you can see, we start out by another RGB to grayscale conversion, because we need the grayscale to change it to the binary. And that's the first 2 lines as I've already gone through in the last one. The grayscale image. This little if statement down here is what converts to binary. It tells the compiler to change if any value is less than 128. It is converted to 0, and else if any value is above 128, it's converted to 255, which is the maximum value of the pixels. And one of them will need to be equal to, otherwise it would not include 128. So when we run it, it looks like this. It's even more a bit like Sin City by Frank Miller. The fun thing is that you can change the volume, and my guess is because there's a it looks fun. There's a brightness, automatic brightness installed into the webcam that alters the feed. You can see the image becomes a bit brighter when I do this, and it's much more apparent in the other image. Plus, I look silly, so that's a bonus. And then filter number 4, the simple brightness. We do the infamous for loop, and it's also relatively simple. This filter. It just a compiler to take each pixel and add 70 to it. for each and every pixel. And it ends up by looking like this. So everything is a bit brighter. But this one here, the two lines, is just a safety precaution. If the output is more than 255, which is white, of course, it'll just change it to white instead. Otherwise, we'll end up with some really weird colors, sort of yellowish. We can just give it a try. If we restart the program. And the other line here is if we change the volume of the brightness down, make it darker, we need this line as a safety precaution to not make it go beneath 0, which is entirely black. You can see here the colors get extremely distorted and weird because it's less. It's more than 255. Makes it a very weird color. And this the white becomes sort of grayish, and everything becomes a bit weird-ish. And as I said before, if the value is beneath 0, it's just sort of changed back to 0. And this one tells the compiler to take the new output value and place it instead of the output value, meaning it just adds 70 to each pixel. And if it's above 255, it changes it back down to 255. That's it. Example number 5 is a simple contrast. And we start out by looping through the pixels. And one for X and one for Y. And here we declare that R red pixels will be stored in the variable R. So this is an integer. And G will be stored in the green pixels will be stored in G, and blue pixels will be stored in B. And that's all the current values of the output image. So to increase the contrast, we have to multiply with another value. In this case, I've chosen 1.9 because it looks pretty good in this kind of light in my apartment. And this here is just an alternative if statement. If the value should be above 255, it's true and is returned as a 255, so it doesn't go over. And if it's false, it'll just return 1.9 multiply with the value of R. I can just show you here. First of all, it looks like this, which is an increased contrast of 1.9. As you can see in this figure here, a photo with high contrast means that there are a lot of pixels on either side. This is close to 255, and this is close to 0. In an image with low contrast, they would all be in the middle here. What we did before with the brightness, we took the entire value of the image and just moved it up. Like we used 70, so this is just moved a bit. All the pixels have added 70 to it, so the entire histogram would just be moved towards the right for increased brightness, and towards the left for decrease in brightness. With the contrast, we just change all the values towards either 0 or 255. Well, not all of them, but they are increased on either side. For high contrast, that is. So, if we were to change on a decrease in contrast, we would just have to, maybe a good value would be 0.5. That means if you multiply value of, say, 255 with 0.5, it would be half, 127.5. And that's basically how the contrast works. And yes, you can see that all the bright colors are made even brighter, and the dark are made a bit darker. An increase in contrast and the difference between the color values. So, the next filter I'll show you is a fun little filter that'll add black and white dots to the video feed. It's called the salt and pepper noise effect, and it's a bit more complicated than the filters we've seen so far, but it's relatively simple. I've made 2 integers called random to pick a value between 0 and 99, and one for either black or white. That is a random value between 0 and 1. And we start out by displaying the original newsfeed here. We've got it here, the output, and the noise is created here. So the percentage of noise, you can set that to 20. That'll create more noise, or even 5%, or I set it to 10% because it looks good. And of course we would have to limit it, otherwise it would be made entirely black or white. So that's what we do here. If it's still under 10%, it will run the if statement. And this one, the random 2, creates sets all the output values to 0, meaning entirely black. And else if it hits 1, and that's randomly generated, or sort of randomly generated, it'll display the pixel value at 255, which is white, and it looks like this. It looks almost like an old stereo television noise that sometimes occurred. We would call it myrkrig in Danish, ant war. And it's a fun little filter. I imagine it could be useful for creating that old television noisy look. Yes. And let me just show you what cranking up the value would mean. If we set it to 50%, that means that 50% of the image would be either white or black pixels. And it looks like this. You can barely notice me anymore, but I'm in there. Yep, that's the salt and pepper noise effect. So the next filter is the classical sepia effect filter. It's almost in every camera you can buy today. This filter is it's very popular. It gives you sort of the illusion of an old photograph. It adds that brownish tint. and the code is also relatively simple. You can see here, you start out by making a classical normal for loop, and hereby we define all the red, green, and blue values. Otherwise, we would have to write it every time. It's just to make it more simple. And to create this sort of brownish tint, I've found some Microsoft approved values online and added it to the filter. So just add to each color value red, set 0.3993 and so forth. Green adds this to each value, and it creates this brownish effect. I don't think it's that good. I wish it could be more brown, but I tried playing around with the values a bit, but it doesn't get much better than that. So it should be another way to do it, or yeah, it's okay. And we output the values, the new values of R, G, B. Yeah, this is just the basic precaution if statements. If the value of R afterwards, after the implementation, is above 255, it's changed to 255, just to a safety precaution. Otherwise, the colors will look strange. Yes, that's the basic sepia effect filter. Relatively simple. And the next filter is our first neighborhood operation, and we'll start out with a 3x3 mean filter, and we created as a float a two-dimensional array that stores the filter, and the mean value is a 1/9 because we have a 3x3, and that's 9, and we want the value to be a 9th of the value of all the pixels, meaning the mean value. And we create a kernel, and we go from 0 to 2, 0, 1, 2, and the same with the this is downwards, and the same with the x-axis, so it's really 0, 1, 2, 0, 1, 2. This is x2, and this is y2. And we define the kernel to have the same value as the mean filter we've just created. So the code for the mean filter is here, and because it has the construction it has, let me just show you. As you can see here, the filter has to start at 1.1, because if we start here, or actually this is where it would start. It has a dimension of 3 pixels. If we were to begin here, it couldn't include these pixels out here. Hence, the edge of the feed will be 1 pixel less. And that's basically what we tell it to do here. To start one pixel in, and not to include the last array of pixels, the bottom. And the same with the weight, not to include the last array of the pixels. And the next for loop tells us to to go towards 3. I mean, because we have the colors RBG, it goes to the value +3. We tell it down here, 3 plus 3 to C, which is that it jumps to the next color in the spectrum, which is from slot 1 to slot 4, which is another red value. And we create the variable of the sum, and we loop through the entire 9 pixels, which is our own filter, and then we find the pixel value. This for all the 3 colors, RBG, and then we weight the kernel to 1,9 right here, meaning that each pixel value will have the mean value of the surrounding, the neighboring pixels, and we'll end up with a sort of blurry. Just have to run it. As you can see on the edge here, the outer pixel, the frame, it's gone because we told the compiler not to include it, and that's one of the downsides of the mean filter, that it gets the picture a bit smaller. There are ways around that. We can use another filter to apply that, but I haven't done that. And yeah, of course, that's the output sum, which is the image. And basically it's the same thing for the disk, the mean disk. Just show you. The filter looks like this. It's exactly the same code, except that we use a larger array, a 2-dimensional array. And go to the codes. There we go. The changes is that it goes from, starts at 3, goes for 7 pixels, you see, and we have 37 here. We have 37 here because we divide the sum with the number of values. Because we have a disk, as you can see here. Now we know that 7 times 77 is 49, but we have some zeros in the corners, which means if we subtract these values, which is 0, we end up with 37, because we have 12 zeros, 3 in each corner. And that's the mean filter, both the disk and the cell, and the mean filter square, 3x3 and 7x7. The code is exactly the same. The array, 2-dimensional array, is just larger. Now let me just show you the disk. It's even more blurry, and that makes sense because the array is larger, so it takes the mean value of a larger area, meaning that the image will get more blurry. And the next one is number 10, and it's a Sobel filter, horizontal, and the filter in itself is something that I found in the book. You can see the filters are up here. There you go. And it is a neighborhood process that orders the lines, and the code is with all the almost all the filters is exactly the same as with the mean filter. Let's just go down. So there we go. The code is a for loop, like I explained in the previous one, except that we apply the Sobel kernel instead. And the result becomes something like this, where the horizontal lines will be very clearly possible, very clear, and the vertical lines will be more subtle. I don't particularly like this filter because I get wrinkles, very deep wrinkles, but we can make them disappear like this. And the other kernel that I wanted to show you is the Prewitt filter. I made it vertical. You can do it both horizontal and vertically. It's simply a different tool doing the same thing of the edge detection. Each filter finds edges that the other can't. So if you apply the two filters in one, then you can do a combination of the filters. The Prewitt filter looks like this, a bit creepy, and you can see the vertical lines are more clearly when I tilt my head. The wrinkles and the code is exactly the same as I've shown you previously, except that we use the Prewitt kernel instead. Both of them are found in the book. So you can see clearly that the lines are found using the Prewitt filter. Yes. And the next filter I like to show you is the median filter. Now this filter is a bit different than the others I've shown you so far. At the beginning we make it grayscale, just for increased performance. And as you can see here, instead of using a predefined kernel to change our output image, our video, we use a vector to store the values, because we have to do the median, and the median is that we have a series of numbers that will range from low to high, and then choose the middle value. And this all happens down here. And to pick, well, at the beginning we use a 3x3 filter, going from -0 to 1. That's 3. So 3 times 3 is 9, and then the median value of that is 4. That's the middle value. And as you can see here, it gives the same blurry effect that the mean filter. The reason that it's really slow, it's lagging like hell, is because it has to make this calculation constantly. It has to, for each and every pixel, find the median value, and it really requires a lot of the computer. That's why it's lagging so much. Another of the filter is the minimum filter, which instead of the median value, takes the minimum value. It's exactly the same code, and belongs to the group of filters known as rank filters. The only difference is actually that it just picks the first value, and it results in the image being really distorted and weird. But you can see the brightness. It's so laggy. And as you can see, the same goes for the maximum filter. The value is instead the last sorted value, which is value number 8, and where the minimum filter makes the image darker, the maximum filter makes the image brighter, because it picks the brightest value. And it looks somewhat like this. Doesn't really qualify as an image anymore. And so, in the category of morphology, I'll show you for style dilation a 7x7, and we start out by defining our red, green, and blue values and their position, and we make it into a grayscale image. And from that we make it a binary image. And again, I've chosen the value of 120 because it fits well with the lighting condition in my apartment. For the dilation, the code is approximately the same as all the other filters I've shown you thus far. As you can see, we look through the values, and what's happening with the dilation is that if we have just one value in the square of 9, and we have the 9 surrounding pixels, if this one is black, or the value of 1, versus 0, which is black. So white, black. It'll paint all the neighboring pixels white as well. Hence dilation. And this image has been applied with a dilation filter through and out, like this. And it looks like this. You can see my binary image down here. And with the dilation filter applied, it'll look like this. You can see that these squares here, it just takes there's some white down here sometimes. Just takes a single pixel, then all the surrounding pixels will be painted white, or get the value of 255 versus 0. So it looks rather weird, kind of cool. Yes, and of course that's what we're doing here. If the sum is less or equal to more or equal to 1, it'll output 255, which is white. Else it'll output 0. We're using the 3 outputs to show you the binary image, and that's why we have 3 video textures. And if we scroll down to erosion, it works. The code is exactly the same. We start out with values, and we make them grayscale, and then binary values, the erosion code. And instead of eroding, we dilate, and it was erosion. So as you can see, it just takes one single value, and if it does not contain a full set of 255 values, 1, it'll change it to black. So meaning that this square, all of them are 1s. So that's the one remaining here. And the neighboring one is also a full square. It's right here. And the last one is up here. All of them, this one here, it does not contain a full set of 1s, meaning it'll be made totally black. And the same goes on for the figure over here. And it looks like this. Sort of the opposite of the dilation. It simply erodes the pixels. If it does not contain 9 1s, it will be made black, meaning that all of them will be set to 0. Another thing you might notice is that the frame is smaller, as with some of the other filters, and that's because we have to start the filter 7 pixels in, and that's why we get this frame. Another morphology is the closing, and that's basically just first we dilate, and then we use the erosion, and the procedure is exactly the same. We start out by making it grayscale, then the binary threshold, then first we apply the dilation, and then we apply the erosion and print out the output. And you can see here our original image, feed, our binary image, our dilation, and the closing with the dilation applied erosion. And a good example, you can see my hand here is really much bigger than the original one. It's not because I just got a big hand. And when we apply the erosion, we sort of close all the eroded, you can see my eye here containing some squares within. We close them by using the erosion down here. And my hand looks almost normal again compared to my hand up here. And the opposite of closing is opening, where we first take erosion and then dilation and apply it in that order. And it's exactly the same, just in the opposite way. And we end up with this. You can see our binary image. First it's dilated and then eroded. And my hand is made smaller. Baby fingers. And this one. And almost back to normal here. You can see with my mouth, it's almost gone here, but here it's dilated. Yeah, that's it. Thank you for watching. Have a nice day.